I have a lot of potential topics on the slides, and we won't go through all of them. Let's see how much time the chairman will give me, and that will determine the exact line of topics. I'll start by shortly giving the main references for the talk. So 4 works in which I was involved, the first and second with my supervisor, thesis supervisor Tilman Wurzbacher, and later with Marco Zambon, and 2 much more recent works with Antonio Mitti and Leili Mamadova also from Leuven, like Marco Zambon. And I should note that the core related literature. So we'll talk about comoments for multisymplectic manifolds, which have been introduced here. And there is this paper, which at the same time independently got the same results as Tilman and me. And later, for the weak moment maps, this notion was defined by Jonathan Herman in 2018, based on some earlier works of Madsen and Swan. So let's get right started. I'll just very briefly remind you of some aspects of symplectic geometry that we'll be interested in. So I assume I shouldn't tell you that, but a symplectic manifold is a manifold equipped with a differential 2 form, which is closed and non-degenerate, where closedness means with respect to the de Rham differential, and non-degeneracy means that the contraction of a vector is a bijection from the tangent bundle to the cotangent bundle at any point. The non-degeneracy condition is a linear one. It is defined over every point, and the closeness condition is an integrability, a differential condition along the manifold. The chief examples of symplectic manifolds are cotangent bundles of practically any manifold. So if you have coordinates qi on a manifold Q, then on T star Q you have a canonical 1 form, which in coordinates looks like sum of pi dqi. And I'm using the sum sign here to annoy the physicists who would prefer Einstein summation notation. And of course, you have its exterior differential d theta, which is just the sum over dpi dqi as a symplectic 2 form. Another example are 2-dimensional manifolds with volume forms, which of course includes T star R, but also something new happening, that is compact manifolds, which of course are never cotangent bundles, so S2 or a torus. And most of those can be realized as another class of examples, being co-adjoint orbits in a Lie algebra. So if we take the dual of the adjoint action on a Lie algebra, then on the whole of the dual of the Lie algebra, there is a Poisson structure, and the orbits of that Poisson structure, the symplectic orbits, are actually symplectic manifolds. Okay, that was just a quick reminder. And now momentum geometry on symplectic manifolds is somehow a type to describe better symmetry of a symplectic manifold. So we start with an ordinary symmetry group that is a Lie group acting, let's say, from the right due to sign conventions on a symplectic manifold, preserving the symplectic form. So for any group element, theta g star of omega is omega. Then we define a moment map to be a smooth map valued in the dual of the Lie algebra, satisfying 2 conditions. The first one is that the components of this comoment actually have as Hamiltonian vector fields the infinitesimal generators of the action. So, and the second one is that the association from M to G star is equivariant with respect to the group action on the manifold, and the co-adjoint action on the dual of the Lie algebra. For what we are going to do multisymplectically, a nicer perspective is actually the dual perspective, which, if G is connected, doesn't lose any information. So for a Lie algebra, the Lie algebra of a connected Lie group, we say that a moment is the following. It is a smooth map, linear map from the Lie algebra to the smooth functions that lifts the infinitesimal action of the Lie algebra on the manifold. So we have the infinitesimal action from G to the vector fields. We have the Poisson algebra of functions with the association f goes to xf here, and we demand a map between those two spaces that projects to the infinitesimal action map. And we can demand this on two levels. The first one is just a linear lift. And the second one is we can demand this map to be a Lie algebra homomorphism, as on the smooth functions, we do have a natural Lie bracket given by the symplectic form. And those two conditions translate directly to being a linear lift and then being a Lie algebra homomorphism. Being by construction, if we look at the condition contraction of some Hamiltonian vector field into omega being df, we automatically get that that the Hamiltonian vector fields actually preserve omega. So so actually we don't map into x of m, but we map into x of m omega here. And the difference between vector fields preserving the symplectic form and Hamiltonian vector fields is a cohomology class. So we'll see that in more generality later, but somehow the obstruction to 1 is some class in the first Theorem cohomology. And not just one class, but one class more or less for every element in the Lie algebra. Just as a quick remark, it will be made more precise and more explicit later. Okay, why do we care for symplectic moment maps, or for those, let's say, better symmetries? Many reasons. One of the reasons is they give rise to conserved quantities, or conservation laws, or Noether theorems, depending on what words you prefer. Another is, very related one, is reduction. And another one is also for quantization of symmetries. And the hope is that in the multisymplectic case, we can use the comoments I'll define in a minute to do the same things. Okay, so let's generalize the definition of a symplectic manifold. Instead of demanding it to be a 2 form, we just say that it's a k+1 form. This is a historical convention because people want one plectic to be symplectic. And this k+1 condition actually is quite convenient at a few places, so we'll stick to that. So it's a k+1 form, which is again closed. By closeness, we mean the same thing as before. And non-degenerate. And here in non-degeneracy, we have to make a compromise. We lose a little bit strength in the general statement. Instead of asking the contraction of a vector into the form to be bijective, we only ask it to be injective, because otherwise we have no chance in general, just due to dimension reasons. So a map is called form is called non-degenerate if the contraction is injective. There is no vector on which this form vanishes completely. The first and the last example are symplectic manifolds and manifolds equipped with volume forms. Those two examples are special because those are actually exactly the examples where this contraction is one-to-one. And somehow this example already generalizes the symplectic example of two-dimensional manifolds with volume forms. So if you want to keep the analogy going, this would be the analog. A second example would be a semi-simple Lie group equipped with its Cartan free cocycle. So on the Lie algebra, we have a free form defined by killing form and Lie bracket. This element is can actually be extended, let's say, left invariantly, and the left invariant extensions turns out to be right invariant as well. So we have a B invariant form on the Lie group. And B invariant forms are automatically closed. So we get closedness for free, and non-degeneracy is a consequence of semi-simplicity. This example plays quite an important role in some sense in the theory of group-valued moment maps. And I think it should be thought of the sort of analog or generalization of the coadjoint orbit example. So the example we're missing so far is the classical phase space example. And this is what we are going to look at now. So, it's called multiphase space and is somehow the original reason why multisymplectic manifolds were investigated as multiphase spaces for classical field theories. So we take any manifold of configurations and consider its multi-cotangent bundle of some level k. And on it, we can define a canonical form exactly in the same way as we had defined the one form on the cotangent bundle. In local coordinates, we should think as follows. A typical element in lambda k t star q is given by some coefficient followed by some dq's with in total k dq's. So dqi1 until dqik. Sorry, it's not very. Okay, and obviously this multi-index I1 to Ik belongs also to the P. And now we take the exterior differential and we get a k+1 form. There is a strong difference to the symplectic setting because here there is no symmetry between the new and the old variables. So in the symplectic case, we had, let's say, diffeomorphisms groups acting extremely transitively, and we can just switch perspectives between configuration space variables and phase variables. Here, they start fulfilling quite different roles. We can, if we want, add to the above form the pullback of any differential form on Q. It's a direct generalization of this magnetic term in symplectic geometry. And from a geometrical point of view, this gives us chromology. So this gives us a way to construct many examples where the form is not exact, which is useful for some cases. And finally, a slightly weird example. We take the six-dimensional sphere, for which it is not known whether it has a complex structure or not. But there is an almost complex structure, J, which is known to be not a complex structure. We take the standard metric and we contract this almost complex structure with it. We get a two form, denoted by eta here. If this almost complex structure were to be complex, that would be closed. But it's not complex. In fact, its differential is even non-degenerate. And thus we have a multisymplectic, a two-plectic form on the S6, so a free form on S6. This example is maybe indicative of the following. We don't in general have topological obstructions. S6 does not have a cohomology in degree 3. So if the symplectic idea that on compact manifolds there are topological restrictions to symplecticity would carry over, this example couldn't exist. Somehow the multisymplectic world is much more flexible, for example, in this sense. Without further elaborating concrete examples, somehow the local theory or the global theory is much more like, let's say, I don't know, Riemannian geometry than symplectic. So there is no flat coordinates in general, no Dabou theorem. The diffeomorphisms groups need not be transitive or locally transitive. We can build multisymplectic manifolds which in different neighborhoods look completely differently. This just as a side remark for the level of flexibility we have. Now, what we wanted to do is we wanted to generalize a comoment map or moment map. And as we saw earlier, for this, we need something like a Lie algebra structure on the observables, on the functions. And we could try to just naively generalize it. So we look at the equation that we had before. df is up to a sign the contraction of xf with omega. And there is a first thing we notice. If we want xf to be a vector field, then f cannot possibly be a function. It has to be a k-1 form, just for degree reasons. Second observation, if we are in a generic degree k, then there is no guarantee that any exact form will be realizable as contraction of something with omega. So what we do is we just say, oh, this was not supposed to happen. Okay. What we do is we just define the Hamiltonian forms as those forms where this equation has a solution. We get for free a projection onto the vector fields, even onto the vector fields preserving omega as before. And we can even define a bracket. So we can just say that the bracket of alpha and beta is omega contracted with x alpha and x beta, and we leave the rest free. This will be a k-1 form. Moreover, a calculation shows it will be Hamiltonian. Moreover, a calculation shows that x of alpha beta will be x alpha bracket x beta. So it even preserves the bracket. So we should be very happy, and we are until we try to calculate the Jacobi identity. So we take some elements, alpha, beta, and gamma. We calculate their brackets in all possible permutations. And what we like to get would be 0, but what we really get is d of omega of x alpha, x beta, x gamma, and then the rest free. So if you are familiar with L-infinity algebras, you already will see the pattern. We have something which is a Lie algebra up to d of something, up to something exact. And always when we see a Lie algebra up to something exact, we search for the L-infinity algebra beneath it. We can actually just go ahead and define this term to be a bracket that takes 3 elements. And then for this tertiary bracket, I don't know, let's say L3, we get a new identity. If it's satisfied, we are in a Lie 2 algebra. If not, we get its identity satisfied up to d of something, and the something there defines us the next bracket. So going through that until the end, we get the following construction. We have a chain complex, which starts with the Hamiltonian forms, and then just the de Rham complex above it. and a set of brackets which are all defined by contractions of Hamiltonian vector fields into the multisymplectic form. And Chris Rogers in 2012 found this algebra and verified that it is a Lie infinity algebra. So it's a definition or theorem of Rogers that the above defined complex with the unary bracket or differential D and higher brackets Li is an L infinity algebra. The formula of being an L infinity algebra is in general a little messy, but basically it just goes through all combinations of brackets that you can make, decorates them with appropriate sums, and wants the result to be 0. So this is an L infinity algebra, and moreover, the projection to the Hamiltonian, to the vector fields, one could also say vector fields preserving omega, which is automatic, is an L infinity homomorphism from a Lie infinity algebra to a Lie algebra. Now, this horrible identity in our construction actually only has 2 terms. There are terms of the type D of a bracket that takes I plus 1 elements and a bracket that takes I elements, and inside it a bracket that takes 2 elements. So this Lie infinity algebra has a very simple type, and the reason for it, or one possible way to explain it, is that it's locally the pullback of a Lie bracket along a resolution. There is I won't go into the details, there is a paper from quite a while ago from Barnish, Fulblade, and Stashev, where they described a procedure of doing this systematically for resolutions. We don't have a case of a resolution with the Theorem complex, but we are close enough. It's locally a resolution, and hence the same procedure still holds and gives us a Lie infinity algebra of a quite simple type. Now, we have a Lie infinity algebra of observables, and the natural definition of a comoment map is just saying that we take our infinitesimal symmetries and we want a Lie infinity homomorphism to the L infinity algebra we have just defined. This in a concrete formula looks as follows. At first sight may be a little messy, but the first condition is the same condition we had before. It is just the compatibility with the projection. And the second condition is what was equivariance before, which is now being an L infinity morphism. And if you look at this equation in more detail, you see that we have F applied to the binary bracket of the Lie algebra. We have some df term, and then we have this term involving omega, which is actually just one of the, up to sign, just one of the brackets of the L infinity algebra. And this is why we can prove the following. We take a multisymplectic manifold with an infinitesimal action, and we can define cohomology classes, Ci, in this tensor product of Chevalier-Eilenberg cohomology and Theorem cohomology. Moreover, a homotopy comoment exists if and only if all those classes are 0. Before I sketch the proof, a brief reminder, in the symplectic case, this recovers the traditional obstruction classes, this one against the linear lift, and this one against equivariance. Now, okay, so for the proof, we could look at the following diagram. I hope it is at least a little readable, where we have, as a second part, just components of the Theorem complex. And as the first part, exterior powers of L0 dual. I remind you that L0 was omega k minus 1 harm of the manifold. So it was some k minus 1 forms, those which have a Hamiltonian vector field. Be careful. So the vertical differential here is a Chevalier-Allenberg type differential. So it's defined by, I take some element and maybe I should write there, and I contract, so I pair any two elements inside it with the binary bracket and just leave the rest as they are and decorate it with a sign. So this is the Chevalier differential with respect to this binary Lie infinity bracket. But this differential does not square to 0. So this is not a double complex in the classical sense. However, our L infinity equations for the Li, for the multi-brackets, where Li, again, was just the brackets of I elements, is some element on the diagonal which which are together 0 if we apply the total differential to them. This might not be.
The thing is when it's just a Lie algebra in general, but in the usual case.
Pardon, I don't quite hear.
Oh, can you hear me now? Can you hear me?
Yes, now I hear you.
Oh, what is this thing if it's a Lie algebra?
So if L0 is a Lie algebra, you mean in the symplectic case?
Right. Is it?
So in the symplectic case, L0 is the Lie algebra of functions with the classical Poisson bracket. And then you just have one element which will probably live here.
Then what are you doing in that case?
So in this case, it's a little bit
construction that classically that we know. Or?
So you can basically you can recover the classical obstructions using this double complex then too, but yeah, it's then somehow so the L2 is an element here, or the Poisson bracket would be an element here, and being a comoment would be exactly described by being a potential in this double complex.
Yeah, there were some classical diagrams to encode the obstruction of a comoment maps, right? But well, maybe it's not the same, so I just cannot recover that. But
I mean, there is another. Maybe we talk about that later, because there are different diagrams you can draw. Maybe one of them.
You're categorizing on.
Sorry again.
I just wanted to see where what you are categorizing on.
Ah.
It's fine.
Okay.
You can continue.
Okay. So this not double complex, however, does become a double complex if we just pull back along any map from G to L0 that lifts the infinitesimal action. So instead of looking at the map LK, we just look at the map F1 star of LK. And now we are in the first component, we are on a Lie algebras. So what we get are some classes which in the total cohomology they define an obstruction class. And the equation to be a comoment map is exactly the same up to some sign conventions as to be a potential for this cohomology class. Hence, basically up to a lot of reordering, potentials in this double complex are exactly comoments, and the cohomology of this double complex after a Kuhnert theorem will be the tensor product of the Lie algebra cohomology and the RAM cohomology. Now, with Antonio, a little more recently, we found a very geometric translation of this obstruction classes. It's given as follows. We just take we take the case of a compact Lie group because then it's easier to write down the geometric picture, but there is a theorem for the non-compact case too. We have a Lie group, a compact Lie group acting on the manifold, preserving the multisymplectic form, and the obstruction that we have written down before, which lived here, translates to an obstruction that we understand very well in the RAM cohomology of M times G. It is just the pullback of omega through the action minus the pullback of omega through the projection. So if you like groupoids, you should like this perspective, which basically tells us that the very algebraic L-infinity theoretic definition is in the end just vanishing of a class in the RAM cohomology of M times G. A brief question to the chairman. It's an online talk, so it is 40 minutes, correct?
Yes, correct.
Okay. So in this case, I would like to end by an application of this theorem, which means that I'm skipping a few slides. Yes, so I would like to finish with this theorem, which is from the same paper with Antonio, where we have looked at the situation for spheres equipped with their standard volume form. And we have concentrated on compact Lie groups, so the above theorem is applicable, which act effectively, preserving the volume. The effectiveness of the action, I think, is a technical condition that at some point we might get rid of. And we have proven that an action of a group that preserves the volume admits a homotopy comoment if and only if n is even or the action is not transitive. So, for instance, the action of SON plus 1 on Sn has a comoment for even spheres, but has no comoment for odd spheres. But for example, the action of SON on Sn, as it has fixed points, always has a comoment. And in the last few minutes, I would go through the idea of the proof. The first observation is that as spheres do have pretty simple cohomologies, there's only one class that really plays a role for us. It's the nth cohomology of the Lie group in that case. And the map that gives us the obstruction is basically the pullback map from Hn Sn to the group. And now we imagine the situation where the action is not transitive. So we would find an orbit so so the group times some point on the sphere, which is of lower dimension than n. So its hn would be 0. Then we, as the pullback map factors through that orbit.
Sorry, why does not transitive mean that this would be of lower dimension? It could be just leave out one point or something.
Yeah, and then the point would be another orbit. So I mean, if your action is not transitive, there will be at least one orbit of lower dimension.
Okay.
So so this would work with any orbit, but we pick one orbit which has lower dimension. The map factors through it, and hence we know that the obstruction class will be 0. So in the intransitive case, we see directly that there is a comoment, and in the transitive case, actually, we just went through the classification of of the spheres as homogeneous spaces for compact Lie groups, and checked by hand that in the odd cases, the obstruction vanishes, and in the even case, which is only here and some cases here, it doesn't. And yeah, we're still looking out for a nice, more elegant proof that it really depends on the parity of the dimension. But so far, we have proven it through this classification. Okay, so as a final remark, if there is no homotopy comoment, even for such actions, then maybe requiring a homotopy comoment is too strong. So n action on a sphere is very symmetric. There is certainly something to be said about it. And this is where the notion by Hermann, weak comoments, comes into play. It does exist for spheres and still yields some sort of conserved quantities, and might be kind of the next best thing if no comoment exists. And with Lely, we have proven existence and classification results for those weak comoments. Okay, I think I'll stop here. Thank you a lot for your attention.
Thank you very much. Okay, we are even a bit early in time, so with, of course, plenty of time for questions. Just
and we are all equally online, right?
We are all equally online, so
not like
go ahead.
Actually, I have one question. Can you say something about the relation of these two, I don't know, quantum field theory or just field theory, something of that sort? Does it have any relation to mathematical physics, which is obvious?
It does come from classical field theories.
Yes.
Basically, it's geometric, and the multisymplectic form is some geometric encoding of the Hamilton, de Donder, Weil, Volterra equations. So that you have in field theory, those equations of the type dH, dq, I don't know, A is equal to sum of dp a mu dx mu, and the second type of equation dH dp mu A is dqa dx mu. So this is somehow historically how Kiofsky and Tulchiev and others have started thinking about those. So starting with this, in this more general set, I mean, so this is an example coming from field theory. I don't know if that answers your question. There's
maybe
a comment about physical applications. Yeah, for example, three-form flux and three-form Riemann-Schwarz flux is regarded as a kind of symplectic form. And we have some momentum up symmetry, gauge symmetry, a target space gauge symmetry, a part of target space gauge symmetry is regarded as momentum up. Here's one physical example.
So maybe just one addition to that. In symplectic geometry, there is this equivalence of existence of a moment and omega coming from an equivariant cohomology class.
Okay.
I think it was due to Bott originally. And this is somehow useful for this perspective of gauge symmetry, because being an equivariant cohomology class means you are a form on the quotient. And the problem is that actually in multisymplectic, this direction works. So if we have an equivariant extension of omega, we always have a moment. You can prove that quite easily through this geometric picture where we have G times M goes to M mod G. Because in the pullback diagram, then both maps would, if you have a form here or on the equivariant cohomology, then it will pull back via projection and action the same way here. But we don't have the other arrow. So just from having a homotopy comoment, we don't necessarily have an equivariant extension. So maybe it does not suffice to have gauge symmetries.
I think, do you remember correctly that you, Thomas, had something about multisymplectic and multi-momentum maps, right?
With Vladimir, we
yeah, right.
probably something related. Yeah,
maybe even before. Didn't you? Is it anyhow related to what Leonid was talking about?
Probably in some way, yeah.
Isn't it true that such a multisymplectic form gives rise to an honest symplectic structure on the appropriate mapping space? A transgression.
Yes, that does work, and it also is well behaved. You get an L-infinity morphisms basically by integration from the Hamiltonian k-1 forms to the function on the mapping space, and also moments. So homotopy moment here transgresses to a moment here.
Why is it necessarily symplectic? Of course, it's a two-form, but why is it symplectic?
I mean, it is automatically closed.
Yeah, sure, but why is it non-degenerate?
Yeah. So for it to be really non-degenerate, I think you have to go to some, not to the whole mapping space, because of course you do have constant mappings there. So in the case of loop spaces, it is non-degenerate on an appropriate knot space. It's written down somewhere in Brzezinski, I think. So it's quite non-degenerate, but maybe in a slightly weaker sense. I mean, I don't know what manifold structure you want to give the mapping space.
In the invariant dimensional case, symplectic structures are rarely fully non-degenerate in the usual sense anyway. I mean, you can only require this weaker statement that the appropriate map is injective. It's rarely also surjective. Maybe it's
okay, but at least in some sense.
What?
At least it should be non-degenerate in some sense.
Well, in this, yeah, in the same sense that multisymplectic forms are non-degenerate. I think that's you get that. I mean, if you think about, like, say if this K is 2, right, then you have a 3 form, so you can transgress it to 2 form on the loop space, let's say. And then if you think about what tangent vectors to the loop space are, it probably translates into the same thing, or the same kind of non-degeneracy condition for the transgressed.
Are you sure?
I
can say what the tangent vectors for the map in space, right? So that's the pullback of vector fields on the target, right?
Yeah. So, well, I mean, I haven't thought deeply about this, but it seems like you can use this the non-degeneracy condition for the 3 form to try to obtain the same.
Okay, maybe. Okay, maybe. Yeah, maybe it's
just saying that this is well, and even if it is degenerate, I think that's I mean, the non-degeneracy condition. It's not even so natural in mechanics. I mean, that's if you look at the this Woodhouse's geometric quantization book. I mean, it starts with this discussion that you always get you get 2 form on the space of initial conditions of your Lagrangian action functional, and that's not always non-degenerate. But that's kind of like the canonical 2 form that you always get in mechanics. But that's just why I mean that was maybe a bit of an answer to your question about what kind of relevance this might have to to physics or field.
Yeah, maybe of this sort. Yes.
Okay. Are there maybe also other questions?
Yes, I would have one. So your L-infinity algebra is infinite dimensional. If I go to the case k = 1, that's still the case. It's an infinite dimensional Lie algebra. But there is also the cotangent bundle of the symplectic manifold, which is a Lie algebroid, a finite dimensional. Is there something similar in the higher case?
So there, in general, I think I'm pretty sure that there isn't. In the concrete case of those multi-cotangent bundles, I think there is a definition of something like higher current algebroid, in some sense, that basically generalizes what you have just described.
But is it what you, Thomas, had, right? Higher current.
Maybe in some other context also, yeah.